We're going to look at the network simplex method. The input consists of an uncapacitated network given by G, B, C, and a feasible tree solution X star determined by the tree having arc set T. As before, we assume the nodes are V1 up to Vn, and the arcs are E1 up to Em. So the method assumes that we already have a feasible tree solution. The problem of finding an initial feasible tree solution will be discussed in a separate video, but for now, let's assume that one is readily available. We'll go through the steps of the method through an example. Here, the box numbers represent the arc costs, and the blue numbers represent the supply variables B. The initial tree solution that we will take will be determined by the tree with arc set E1, E2, and E6. And the values of X star are given by 2 on E6, 2 on E2, 1 on E1, and 0 everywhere else. And this is a feasible tree solution because all entries are non-negative. Now, step 1 says we have to form this set N, and it consists of all the arcs not in the tree. So E3, E4, and E5 are in N. In step 2, we have to solve for Y1 up to Yn. Here N is 4, so that Yn is 0, so the Y value at V4 is 0. And for each arc in the tree, the Y value at the tail minus the Y value at the head is equal to the cost on the arc. So if we look at the arc E6, we need the Y value at V3 minus the Y value at V4 to be equal to 4. So we need something minus 0 to be 4. So that has to be 4. And now, if we move to E2, we need the Y value at V1 minus the Y value at V3, which is 4, to be equal to 3. 3 is the cost on the arc E2. So we need Y1 to be 7. And finally, if we look at our E1, we need Y1 minus Y2 to be 2. So Y2 is 5. In step 3, we want to find an arc EK not in the tree such that the Y value at the tail of EK minus the Y value at the head of EK is bigger than the arc cost on EK. So we'll go through the arcs one by one. So for E3, we're looking at Y2 minus Y3. And Y2 is 5. And Y3 is 4. And that's 1. And that's equal to the arc cost on E3. So we move on to E4. And we're looking at Y3 minus Y2. And that's 4 minus 5. And that's negative 1. And that's equal to the arc cost on E4. Next, we look at E5. We're looking at Y2 minus Y4. And that's 5 minus 0. And that's 5. And that's bigger than 2, which is the arc cost on the arc. So we're going to choose K equal to 5. And in step 4, we're going to add in the arc EK and look for a cycle. So I'm adding in E5. And we can see that the cycle consists of all 4 arcs in red. E1, E2, E5, and E6. And this cycle is not a dicycle. In step 6, we need to form this set R. And what we do is, we traverse the cycle in the direction of the arc that we have added. So we traverse the cycle in the direction of E5. And if we encounter an arc that points to an opposite direction, we add it to R. So as we travel along E5, we see that E6 is pointing in the opposite direction. Same for E2, but not for E1. So R will consist of E2 and E6. And we set theta to be the minimum flow value on the arcs in R. Now, both values are 2, so theta is 2. And we have to choose an index, lowercase r, so that the flow value on the arc ER is precisely theta. We have 2 choices here. Lowercase r can be 2 or 6, and we're going to choose 2. In step 7, we update our flow. So for every arc in the cycle that is not in R, we increase by theta. And for those that are in R, we decrease by theta. So the flow values on E6 and E2 will be decreased by 2, and the flow values on E1 and E5 will be increased by 2. And this is what we get. And we replace our tree by including the arc EK, in this case is E5, and removing the arc E lowercase r, in this case is E2. So this is our new T, and it determines a feasible tree solution given by the values in red on the arc. So we can start a new iteration. Now the set n will consist of E2, E3, and E4. And we need to compute the y values again. So y4 is 0, y3 needs to be 4, y2 needs to be 2, and the y1 needs to be 4. We can quickly see that y3 minus y2 is bigger than the arc cost on E4. So we're going to choose k equal to 4. And we add this arc in. And we now have a cycle consisting of the arcs E4, E5, and E6. And in this case, R is just E6, because if we travel along the cycle, only E6 is pointing in the opposite direction of our travel. And so theta is 0, since the flow value on E6 is 0. And lowercase r will be 6, because this is the only choice. And since theta is 0, none of the values of x star is going to change. And the new T will include E4, but not E6. And we start a new iteration. So n is going to be E2, E3, and E6. And for our new y, y4 is 0, y2 is 2, y1 is 4, and y3 is 1. And one can now quickly check that there's no k such that y at the tail of ek minus y at the head of ek is bigger than the cost on ek. And so what we have here is a minimum cost feasible flow. There's still a question to be answered. Does this method terminate? It is conceivable that after a number of iterations, we come back to the same set T. And that phenomenon is called cycling. We know that cycling can occur in the simplex method. But is it possible for cycling to occur in the network simplex method? And the answer is yes. And the first example is found by William Cunningham. So we do need to have an anti-cycling rule. And Cunningham did propose one. Now, of course, we can apply Bland's anti-cycling rule. And it's to choose the smallest index in step 3 as well as in step 6. And if we do that, that will guarantee that we won't run into cycling.